Hey everyone, Mr. Schachter here to examine the patterns within derivatives of sine and cosine, and also to calculate the second derivative of a basic trig function other than sine and cosine, because we're going to find that sine and cosine are predictable. Let's start by examining the derivatives of sine x. Okay, so we know that the first derivative, which I'll call just y prime, is equal to the derivative of sine x, which is just equal to cosine x. Okay? And then if I go one more derivative, that's the second derivative, I'm going to do the derivative of cosine, which is negative sine x. If I go a third derivative, I'm taking the derivative of negative sine x. So the derivative of negative sine x is just negative cosine x, because the derivative of regular sine x is cosine x, and the derivative of the negative just kind of follows down, giving me negative cosine x is the answer. And if I go a fourth derivative, 1, 2, 3, 4 primes, the derivative of negative cosine x. Well, remember that whenever you take the derivative of anything with a co, the answer is negative. But there's already a negative here, which is going to turn this into positive. And the derivative of cosine is just going to go back to sine. So I know that after 4 iterations of a derivative, I have the sine x back to normal. So if I go a fifth time, we'll just call it y to the fifth power for now. We'll do like y 5 prime or something, I guess. Now I just repeat myself, because now I'm back to sine. The derivative of sine is cosine. And then if I do a sixth prime, I know it's negative sine. And if I do a seventh prime, I know it's negative cosine. And if I do an eighth prime, I know it's equal to sine, and then I repeat myself again. So every 4 derivatives tends to repeat itself, and this is true for cosine x as well. If you wanted to prove it to yourself, write down 4 iterations of the cosine derivative. You'll end up back at cosine. So let's use what we've learned to find the 50th derivative of sine x. To solve this problem, what you really have to do is ask yourself, this 50th derivative, how many times does 50 go into 4? Because if I figure that out, I know what iteration to kind of start with. So I know that 50 goes into 4 an even number of times of 12, right? And I think what remains is 2/4, so 0.5. So I'm just going to call this 12 and 2/4. All right, so I'm just going to move this over. 12 and 2/4. So what that really means is, let's assume that I did 12 iterations of the sine x derivative. So, I'm doing iteration 1, iteration 2, iteration 3, iteration 4, reset, 5, 6, 7, 8, reset, all the way down, so that these 12 derivatives are actually meaningless, because now I'm back to sine x. This remainder is really the important part. The remainder was 2/4. So that means I'm going to do 2 more derivatives starting at the beginning of the problem. So if I go back and analyze my derivatives, we'll use this right now. If I go 1 more derivative, that brings me down to the cosine x. If I go 2 more derivatives, that brings me to a negative sine x. So I know the 50th derivative of sine x is negative sine x. Okay? Let's take a look at a second derivative of a basic trig function, secant x. So I know the first derivative of secant x is equal to secant x tan x, right? In order to find the second derivative, I need to now use the product rule, where I'm multiplying a secant x and a tan x. So the product rule says to take the first function, secant x, and multiply it by the derivative of your second function. So the derivative of tan x is secant squared x. And then I'm going to add the second function, which is tan x. And I'm going to multiply by the derivative of the first function. The derivative of secant x is secant x tan x. Okay? So I could clean up my second derivative by saying it's equal to secant cubed x plus secant x tan squared x. So the moral of the story here is your other 4 trig functions, excluding sine and cosine, those derivatives don't repeat each other. Sine and cosine are the only ones that start to tend to repeat each other. If you have to find multiple derivatives of the other trig functions, you've got a bit of work to do.